In this video, we'll use the Gram-Schmidt orthogonalization procedure to obtain an orthonormal basis to represent a set of signals. In particular, we will try to process these 4 signals to obtain an orthonormal basis. The order is arbitrary, and in this case, we will process the signals sequentially. We will start with the first signal, S0, which is this one, and the first element of the basis is obtained just by normalizing this first signal. We need to compute the energy of the signal, for instance, by integrating its square modulus. This is the square modulus, the integral is 2, and the first element of the basis is just S0 divided by the square root of its energy, which is this signal phi 0 that we have here. In the next step, we process the next signal, S1 of t. We have one element. In the basis, it is necessary to compute the projection of S1 over phi 0. The corresponding coordinate is obtained by the inner product between S1 and phi 0, integral of the product between S1 and phi 0. We need to integrate this product that we have here. The integral is 0, and this means that S1 is orthogonal with phi 0. It is necessary to remove to S1 the projection over phi 0, in this case is null, and D1 is equal to S1. And last step is normalization. It's necessary to obtain the energy of D1 by integrating, for instance, a square modulus of D1, which is this signal. The energy is 2, and the second element of the basis is D1, which in this case is equal to S1 divided by a square root of its energy. And this is phi 1 of t. This is the second element of the orthonormal basis. In the next step, the next signal is processed. In this case is S2 of t. Now we have 2 elements in the orthonormal basis. It is necessary to calculate the projection of S2 over these 2 elements. The coordinates with respect to phi 0 and with respect to phi 1 are obtained by the inner product with phi 0 and the inner product with phi 1. Just by integrating the product of S2 with phi 0, which is this signal, and the integral of S2 with phi 1, which is this signal. The first integral is 0, the second integral is minus a square root of 2. Then a signal D2 that is orthogonal to phi 0 and phi 1 is obtained by subtracting to S2 the projection of this signal with respect to phi 0 and with respect to phi 1. A to 0 times phi 0, in this case we have 0 for A to 0, and minus a square root of 2 times phi 1. D2 is this signal that we have here. Once that we have D2, last step is just normalization. The energy of D2 is computed by integrating, for instance, its square modulus. Square modulus of this signal is like that, and the integral is 1. D2 has energy equal to 1. And last step in general is to normalize D2 by dividing it by its by the square root of its energy, and in this case we obtain the third element of the orthonormal basis, phi 2 of t. And finally, the last signal is processed in the last step. Now we have 3 elements in the orthonormal basis. It is necessary to compute the projection of S3 with respect to these 3 elements by computing the coordinates with respect to phi 0, phi 1, and phi 3 by means of the inner product with phi 0, phi 1, and phi 2. And this is equal to the integral of the product between S3 and phi 0, phi 1, and phi 2. This is the first signal, the second signal, and the third signal that we have in these 3 products. The integrals are respectively a square root of 2, 0, and 1. And then we obtain a signal D3 that is orthogonal to phi 0, phi 1, and phi 2 by subtracting to S3 the corresponding projections with respect to phi 0, phi 1, and phi 2. By subtracting a square root of 2 times phi 0, 0 times phi 1, and 1 times phi 2. D2, D3 in this case, sorry, this is D3. D3 in this case is 0, is a null signal. This means that we can write S3 as a square root of 2 times phi 0 plus 0 times phi 1 plus 1 times phi 2. And this means that it is not necessary to include a new element in the basis to be able to represent S3 as a linear combination of the elements in the basis. Therefore, this element will not generate a new element of the basis. After obtaining, in this case, this orthonormal basis of dimension 3, it is possible to represent these 4 signals as a linear combination of the 3 elements of the basis. Each signal will have associated a vector with 3 coordinates. The coordinates with respect to phi 0, to phi 1, and to phi 2. And here you can see the coordinates for the 4 signals. This is the vector representation of the 4 signals that in this case can be plotted in a 3-dimensional plot like the one that we have in this picture.